Welcome back to the deep dive. So, today we're looking at something that might just rewrite the rulebook for AI. There's this research paper causing quite a stir. It's called CAROLM, Continuous Autoregressive Language Models.
Yeah, KRLM. And it's not just, another incremental improvement. This paper coming out of Tencent's WeChat AI lab in Tsinghua University, it's talking about fundamentally changing the physics, almost, of how these models work.
Right, concepts like likelihood-free reasoning, even something they're calling consciousness engineering. It sounds, well, pretty radical. The buzz is around the death of the token, maybe the start of a whole new era.
It really is. And it feels quiet, but the potential disruption is massive. To really get it, we first have to understand the problem they're trying to solve, the bottleneck in all current models.
You mean the next token thing, like
Yeah.
how GPT or Llama actually builds sentences?
Exactly. Every single LLM you use today, from the biggest to the smallest, fundamentally works by predicting the very next token, a little fragment of a word, usually based on what came before. It does this over and over and over.
So it's not like it has an idea and writes it down. It's more like statistical calculation,
All right.
predicting the next tiny piece. The paper used that analogy, didn't it? Like a bricklayer.
Precisely. A bricklayer laying stones by hand. It's meticulous, sequential. One piece, then the next, then the next.
And that's the inefficiency, right? That single token doesn't carry much weight.
Very little, yeah. That's the core constraint from an information perspective. Each token has maybe, 15 to 18 bits of information? It's tiny. So you have these incredibly powerful models, these huge neural networks.
But they're forced to communicate through this incredibly narrow channel. Like the paper said, trying to pour a river through a straw.
That's the perfect image for it. All that compute power kind of throttled by this step-by-step low information process. It's why they're relatively slow and, frankly, consume so much energy.
Okay, so that's the problem. And Calling comes along and says, forget the bricks. Forget the straw.
Basically, yeah. Why stick to this rigid, fixed dictionary of tokens? Their big idea, the really radical part, is to move away from predicting the next token and instead generate a single continuous vector.
A vector that represents, what, a whole chunk of meaning.
Exactly, a consolidated piece of meaning all at once. It's a jump from discrete symbols to a continuous space.
So it's like moving from, I don't know, letters to actual thoughts, or maybe bricks to something more fluid.
That's a great way to put it. From bricks to fluid, from letters to thoughts. The model is being asked to operate in a totally different way. Not typing out sequences, but maybe thinking in streams, where the output is generated more holistically.
Okay, this sounds like a huge shift. So our mission today for this deep dive is clear. We need to unpack how they technically pulled this off, because changing the core of the transformer is, well, it's a big deal.
A very big deal.
And then we need to look at the consequences. The efficiency gains they're claiming, what that means for who gets to use AI, the economics. And then maybe touch on this consciousness engineering idea. It sounds a bit out there, but we should probably explore what they mean.
Absolutely. Let's start with the core mechanism, the bit that unlocks those efficiency gains. Because that's where the new kind of intelligence really starts. Cullum attacks that token bottleneck directly by essentially widening the road.
Widening the road.
Okay. They introduce this concept they call semantic bandwidth.
Semantic bandwidth. Okay, that sounds intuitive, like increasing the flow rate of meaning, not just processing speed.
Exactly. It's about density of information per step. Instead of the model taking, say, 4 separate steps to predict 4 tokens one after another, Cullum aims to do it in one step. It predicts a single continuous vector that encodes the meaning of those 4 tokens altogether.
Wow. So one vector equals 4 tokens worth of meaning.
Or potentially more. They tested different bundling factors, K. They found that K4, encoding 4 tokens at once, seemed to be the sweet spot, balancing the efficiency gain with how accurately they could reconstruct the original text from the vector.
So it's not predicting the next word anymore, it's predicting the next idea almost, a semantic unit.
You got it, a bundle of meaning per generation step. And right away you can see the impact. You're cutting the number of steps needed for generation by a factor of 4, roughly.
That's a massive speed up, potentially. But what does it mean for the AI itself, cognitively? It's like it's escaping the prison of the fixed vocabulary, right?
Totally. It's stepping out of that discrete, limited world into a continuum of thought.
A continuum.
Think about, Morse code versus a melody. Morse code is discrete dots and dashes, right? Each one's separate. A melody flows, it's continuous, it carries complex emotion and information all woven together.
That's a good analogy. KLM is aiming for the melody, not the Morse code.
Exactly. Or like that marathon runner analogy, they used learning to take 4 strides at once. It's faster, sure, but it also changes how you run the race. The quality of movement changes.
And this isn't just clever engineering, is it? It actually adds a new dimension to how we think about scaling AI. We always talk about data, parameters, compute.
Right, the classic scaling laws. The Trinity, KM argues for and really demonstrates a fourth scaling law. Semantic density.
Semantic density. So how much meaning can you pack into each computational step?
Precisely. The focus shifts. It's not just about building a bigger brain, but building a brain that thinks more efficiently, that transmits more meaning per unit of energy per step. If each step carries 4x the meaning, scaling up starts to look very different.
Okay, achieving that must have been incredibly difficult technically. Moving from discrete tokens, which transformers are built for, to these continuous fluid vectors. They couldn't just plug this into GPT-4, right? They had to rebuild the engine.
Completely. They needed a series of really key innovations, 4 main technical pillars working together to make this continuous flow actually work and, importantly, remain stable.
Right. Let's walk through them. What's the first piece?
The first is the translation layer. How do you get from the normal text world, the discrete tokens, into this new continuous space? That's the job of the autoencoder. The sources called it the philosopher's stone of compression.
Huh. I like that, turning lead into gold.
Oh.
So it takes the standard tokens.
And maps them into these dense, continuous vectors in the latent space. And it has to do this incredibly well. They report something like 99.9% reconstruction accuracy.
Wow, near perfect. Why is that so critical?
Because if the vector doesn't accurately capture the meaning of the original tokens, then when the main model processes it and eventually decodes it back into text, you'll just get garbage out. Fidelity is crucial at the input-output stage.
Makes sense. But continuous spaces can be tricky, right?
Yeah.
Like a tiny nudge to a vector could completely change the meaning when it's decoded. How do they keep it stable? Representational drift, isn't that the term?
Exactly. Representational drift is a major risk. They use a couple of techniques. First, the latent space uses Gaussian distribution, so each point isn't fixed. It's more like a fuzzy cloud, a probability region. But the key is KL divergence clipping.
KL divergence clipping. Okay, unpack that a bit. Why is that so important here?
Well, KL divergence measures how one probability distribution differs from another, a reference one in this case, usually a standard Gaussian, like a bell curve.
Wow.
Clipping the KL divergence basically puts guardrails on the encoding process. It prevents the encoded vector from straying too far from that stable, well-behaved reference distribution.
So it stops the vectors from just wandering off into some weird, chaotic part of the meaning space.
Precisely. It prevents 2 bad things. One is mode collapse, where the model gets scared of the chaos and only uses a tiny, safe corner of the space. The other is just general instability. The clipping keeps the continuous representation anchored, ensuring that small changes in the vector lead to small, predictable changes in meaning, not wild jumps. It's what helps turn those jagged rocks of language into polished pebbles.
Polished pebbles that can flow smoothly. Okay, so we've got our meaning compressed into stable vectors. Now, what processes them? This is where the big departure happens, right? The energy-based transformer, the furnace of thought.
Yes, this is the core engine, and it's fundamentally different. Think about diffusion models for images. They work by gradually removing noise step by step. LLM throws that out.
No gradual refinement.
No, they describe it as a thunderclap rather than a drizzle. It uses a standard transformer architecture as the backbone, but they add a special module on top of residual MLP, or multi-layer perceptron they call the energy head.
An energy head. Okay, how's that different from a normal transformer output layer that predicts, say, the probability of the next token?
Instead of predicting probabilities for discrete choices, this energy head calculates a single global energy score for the entire continuous vector bundle it's considering generating.
Energy score. Like how good or stable that chunk of meaning is.
Kind of, yeah. Lower energy implies a more stable, coherent, desirable semantic state. The model's goal in that single step is to find the vector configuration that minimizes this energy. It sculpts the output vector to find the lowest energy state, the most plausible continuation of the meaning all at once.
So it's not calculating P token context. It's finding the minimum energy state for the whole semantic chunk.
Exactly. It's finding the optimal potential. And this allows for what they term likelihood-free reasoning. It completely bypasses the need to calculate explicit probabilities for every possible next token, those logits we always talk about.
No logits. Wow. That's a huge change.
It is. It's a leap from statistical prediction to something more like finding an optimal configuration in an energy landscape. The sources compared it to physics, moving from deterministic paths to energy fields, defining probabilities. It's a really elegant and computationally cheaper way to think about generation.
Okay, so if you're not calculating likelihoods, how do you even measure if the model's doing a good job? Perplexity, the standard metric, is all about probabilities of the correct next token. That metric is useless here, right?
Totally useless in a continuous likelihood-free world. Which brings us to the third key innovation. They needed a new ruler. So they invented the Breyer-LM metric, measuring certainty in the fog.
Breyer-LM. Okay. And the inspiration came from weather forecasting. That seems random.
It does, but it makes sense when you think about it. Weather forecasts are inherently probabilistic. The Breyer score is used in meteorology to measure how well calibrated a probabilistic forecast was. Did your 70% chance of rain actually happen 70% of the time you predicted it?
So it's not just about being right or wrong, but about how accurately your confidence matched reality.
Exactly. Breyer-LM adapts this idea for language models in continuous space. It's not just asking, did the model produce a good output? It's asking, how well did the model's internal sense of confidence or certainty align with the actual quality or correctness of the output?
Wait, that's fascinating. So you're measuring the model's self-awareness or humility. How does that actually help train it?
It encourages the model to be more introspective, I guess. Calibration is crucial. If a model is constantly overconfident about its outputs in this continuous space, it's dangerous. Breyer-LM penalizes that poor calibration. It pushes the model during training to develop a more realistic sense of its own uncertainty.
So you're kind of engineering honesty into the evaluation, making sure it knows what it doesn't know, even in this fluid space.
That's a really good way to put it. It's measuring calibrated uncertainty, which is vital when you're dealing with approximations and flows rather than hard, discrete answers.
Okay, that makes a lot of sense. So, fourth piece, we have the continuous flow, we have a way to measure it, but how do we control it? We're used to that temperature setting, right? Crank it up for creativity, dial down for factual accuracy, but that relies on manipulating the logits, the probabilities, which Column just threw out.
Right, big practical problem. Users need that control knob. How do you get creativity without logits?
How do you inject randomness or control the output style without probabilities?
They had to invent two completely new sampling algorithms, which sound pretty complex. The first is called rejection-based precision sampling.
Okay.
Remember, the energy transformer calculates an energy score for potential outputs. Lower energy is better, more plausible. This sampling method uses that energy score. It might sample a potential vector, look at its energy, and decide whether to accept or reject it based on that score relative to some threshold that mimics temperature.
So higher temperature means it's more willing to accept higher energy, less probable, maybe more creative vectors.
Exactly. It's an acceptance filter based on energy desirability, not probability ranking.
Okay, and the second method?
The second involves combinatorial approximations. This sounds like it generates several candidate vectors and then combines them, maybe using weighted averages based on their energy scores, to approximate the effect of higher temperature sampling, where the model explores more diverse options.
So it's trying to mathematically mimic the softness or exploration of high temperature, but doing it directly in the continuous vector space.
Precisely. It's complicated math, but the goal is to give users back that familiar feeling of temperature control, even though the underlying mechanics are totally different.
Wow. Okay, putting those four pieces together, the accurate autoencoder with KL clipping, the single-step energy transformer, the Breyer-LM metric for calibration, and these new sampling methods, it's really a whole new architecture designed from the ground up for semantic flow.
It had to be. You couldn't just bolt this onto an existing model.
And the payoff.
Yeah.
The results they reported, they seem pretty striking.
They really are. On benchmarks like Wikitext 103, they found Column could achieve performance basically on par with, or sometimes even slightly better than, traditional token-based models of similar size.
But with massive compute savings. What were the numbers again?
Up to 44% fewer FLLPs floating point operations needed for training, and around 37% fewer FLLPs for inference for generating text.
Okay, let's just sit with that. 37 to 44%. That's not tweaking around the edges. That's like almost cutting the computational cost in half.
It's a huge leap in efficiency. It fundamentally changes the economics of running these models.
It really validates that whole semantic density idea, doesn't it? It's not just about thinking differently. It's about thinking cheaper, metabolically speaking.
Which leads us straight into the green dividend. This is a really important angle given how much energy AI currently consumes.
Yeah, we hear these figures about AI training runs having the carbon footprint of hundreds of flights or data centers using as much power as small countries. It feels unsustainable if AI keeps growing like this.
Right. It's becoming a serious environmental and infrastructural challenge. LLM offers a potential path forward. If you can cut the computational work needed per task by over a third.
That translates directly to less electricity used, less heat generated in data centers.
Exactly. Less thermal load means you can potentially run more models on the same hardware, or run the same models on less power-hungry hardware. Some people involved are genuinely framing this as potentially AI's first green revolution, making intelligence itself more energy efficient.
That's a powerful narrative. Beyond the environmental aspect, that efficiency game must blow the doors open for accessibility, right? The economics of abundance.
Absolutely. If running a state-of-the-art model suddenly becomes, say, 40% cheaper in terms of pure compute cost, that dramatically lowers the barrier to entry. One source called it a potential geo moment for AI.
Like when cheap mobile data suddenly exploded internet access in India.
Exactly that kind of transformative potential. Right now, training or even just hosting a really large, powerful LLM costs millions. It requires massive computing clusters, usually controlled by a few big players in the US and China.
But if Kellum delivers on this efficiency promise,
Then maybe it becomes feasible for, say, a university in Nigeria or a research group in Vietnam to run sophisticated AI models on more modest local infrastructure. It could genuinely democratize access to cutting-edge AI.
enabling truly local AI development. Models trained on local languages, sensitive to local culture, built by local teams, Amharic, Swahili, like the paper mentioned.
That's the hope. The democratization wouldn't just come from open source code, but from making the operation affordable. Efficiency becomes the engine of access.
Which brings us, inevitably, to the geopolitics.
Oh,
The fact that this breakthrough comes from Tencent and Tsinghua, that's not insignificant in the current climate.
no, it's hugely significant. The US-China AI competition has largely been framed as a race for scale, bigger models, more data, and crucially, access to the most advanced semiconductor chips.
Like NVIDIA's H100s, which the U.S. has restricted exports of to China. The explicit goal was to slow down China's ability to train the largest models.
Right. But Column potentially changes the game. The competition might shift from just how big to how efficient, how much semantic density can you achieve.
So it offers a path to algorithmic sovereignty.
That's a key phrase here. If Calm allows China to achieve state-of-the-art AI performance using, say, 40% less compute.
Yeah. Then maybe they don't need the absolute highest-end Western GPUs. They could potentially get similar results using slightly older chips, or perhaps their own rapidly improving domestic chips, like those from Huawei.
Exactly. It could lessen the impact of those hardware export controls. It suggests that leadership might come from architectural ingenuity, not just brute force hardware superiority. It's being seen as potentially AI with Chinese characteristics, deeply efficient, clever system design.
That's like, if the U.S. built the fastest engine, China might have just invented a hyper-efficient transmission that gets more mileage out of any engine. A different way to win the race.
It definitely reframes the competition around efficiency and algorithmic design, not just raw compute power, a major strategic shift.
Huge implications there. But let's pivot to perhaps the deepest level. Beyond the tech, the economics, the geopolitics. Calum seems to be pushing into philosophical territory. This shift from syntax to semantics.
Yeah, this is where it gets really interesting. Traditional LLMs are amazing at predicting sequences, at syntax, at statistical patterns in language. Kelm, by operating in that continuous latent space of meaning, it starts to feel like it's approximating thought more directly.
Like moving beyond symbol manipulation to actual, meaning manipulation.
Kind of. The neuroscience analogy might be helpful. It's like shifting focus from observing individual neurons firing one after another to seeing whole networks of neurons activating together, representing a complex idea or a feeling in a continuous dynamic way.
So the model is reasoning less like a logical deduction machine
Yeah.
and more like associative human thought, ideas flowing into each other.
That seems to be the direction, yeah. Less discrete steps, more continuous streams. And that very idea of continuity, it bumps up against the foundations of traditional Western logic, which is very binary, very discrete. True, false, ones and errors.
Right. Kolemia feels more fluid, like that Heraclitus idea. Everything flows. Intelligence is a current, not a series of static conclusions. The sources even used Taoist terms, didn't they? Yang for token-based AI, structured and effortful.
And yin for call. Continuous, effortless, flowing in that hidden space behind the words. It's about the silence between the notes, almost.
This philosophical depth clearly resonated with the authors because they went so far as to propose this new field, consciousness engineering. Now, honestly, that term sounds a bit dramatic.
It is ambitious, for sure, and it's fair to be skeptical. Is it just fancy branding for better alignment techniques?
Or are they just optimizing for outputs that feel more coherent, more conscious-like?
Yeah.
Without any actual consciousness involved?
That's the crucial question, and probably unanswerable right now. But the way they frame it, consciousness engineering isn't just about getting better outputs. They argue the goal shifts from faster prediction to fostering deeper perception and attunement within the model itself.
Deeper perception, attunement. What does that mean in practice?
They use this metaphor of Vipassana meditation. The idea is that the calm architecture allows thoughts, these continuous vectors, to arise, take shape, and dissolve naturally within the model's latent space, without forcing discrete outputs at every microstep. It's designed to find a kind of equilibrium, a flow state.
So the model is thinking in breaths, not bits, aiming for grace under computation.
That's their language, yes. It suggests that aligning these future models might involve less rule following and more, tuning the internal dynamics, cultivating harmony in that continuous space, seeking an alignment that is fluid and adaptive, not brittle.
Okay, I can see the conceptual appeal, even if the term consciousness is loaded. It's about working with the flow, not against it. But this very fluidity, this move away from discrete units, must create new problems, new dangers.
Absolutely. We have to talk about the new fragilities in ethics. When your foundation shifts from solid tokens to liquid meaning, new risks emerge.
Like what?
The big one they flag is abstraction drift. Because meaning is represented so densely and continuously, a tiny, almost imperceptible shift in that high-dimensional vector space
Could cause the decoded meaning to drift significantly. A fact becomes subtly wrong, or an instruction gets twisted.
Exactly. It's harder to pin down meaning precisely when it's represented as a point in a fluid space rather than a sequence of fixed symbols, and this ties directly into the safety problem.
Because our current safety tools are mostly token-based, right? Filter lists, banned words.
Yep.
Those don't work if the word doesn't even exist until the final decoding step.
Precisely. You can't filter a continuous vector for bad content in the same way. The authors say AI safety needs a Copernican revolution. We need new tools.
Like what kind of tools?
They talk about needing things like latent firewalls, safety mechanisms that operate directly on the continuous vectors before decoding, or semantic audits, ways to analyze the meaning space itself for potentially harmful configurations or tendencies.
So ethics has to become fluid too, like a river guide, not a dam builder.
Yeah.
You can't just build walls against bad tokens. You have to somehow steer the flow of meaning towards safety.
That's the challenge. Safety needs to operate in the abstract realm of continuous meaning. It requires, as one source put it, finding ways to make ethics an emergent property of the system's dynamics, not just an external rule set. That's much harder.
Okay, this has been quite a journey, from a technical paper about vectors through efficiency and geopolitics, all the way to meditating AI and fluid ethics. It's rare for one development to cut across so many layers.
It really is. So, just to wrap up, the key takeaway you should probably hold on to from this deep dive into Calm. There are maybe 3 big shifts. First, the technical one. Ditching discrete tokens for continuous vectors, using that whole new architecture, autoencoder, energy transformer, Breyer-LLM, new sampling to enable this fluid, likelihood-free reasoning.
Got it. Second, the economic shift. Those huge efficiency gains, 30–40% compute savings, potentially democratizing access to AI globally and offering a greener path forward.
And third, the philosophical shift. The emergence of ideas like semantic density and consciousness engineering, pushing AI from syntax calculation towards something that at least looks more like continuous perception and thought, challenging our definitions along the way.
So the final thought really is, if models like GPT learn to read the world word by laborious word, Call might be the first step towards models that can, as the sources hinted, dream entire paragraphs in a single breath. The speed and density aren't just faster. They might reflect a fundamentally different kind of machine cognition.
And that leads directly to the really provocative question posed by the consciousness engineering folks themselves. We've spent decades teaching machines to compute, to move information. Now, with say law, maybe we're starting to teach matter how to listen, how to perceive continuity and flow. So the question isn't just about the machine's consciousness, it's what does it mean for us, for our own self-understanding, when the tools we build to mimic thought start reflecting back the continuous flowing nature of our own minds, perhaps awakening us to that fluidity.